Okay, Assalamualaikum warahmatullahi wabarakatuh and very good afternoon to all of you. We are still in the single phase full wave rectifier. But according, if you refer to the course outline, this week we should already go for the DC motor drive, okay, using rectifiers. But I think we will finish this single phase full wave and also three phase rectifiers by today, inshallah. And by our next class, which is on Thursday, we will go to the DC motor drive using rectifiers. Okay, so I think without any further ado, so we continue our class. So this is a single phase control full wave rectifiers using R load. Okay, so in our previous class, we have looked on the single phase full wave uncontrolled, which is we are using full bridge. Okay, and for this for today, so we are looking at how the behavior of the circuits when we are using SCR. Okay, we replace the diodes with the thyristor, or we call also SCR, silicon control rectifiers, where we control the firing angle, or sometimes also we call as a delay angle. So the resulting of using this SCR, so it will the output of the voltage, okay, will be an adjustable DC output voltage, okay, and also adjustable current. Okay, and if you also noted that if there is no delay angle, okay, meaning that the delay angle is set to 0, okay, if the delay angle is set to 0, so the rectifier behavior looks like is a diode rectifiers, okay, because they have no delay angle. Okay, so next slide. So this is actually the circuit. We are using full bridge rectifiers as our examples. Okay, so you can see we have SCR, T1, T2, T4, and T3. Sorry, T3 and T4, and the arrangement is similar to the previous circuit. Okay, in the full wave with the diode, because they work in pair. Okay, so T1 and 2 will turn on, okay, forward bias, and then give the signal. Okay, and so it will, both of the SCR will be operated. And then for the negative cycle, another SCR, which is T3 and T4 will operated. Okay, and depends on the delay angle. So you will have, for example, the delay angle is actually at 60 degrees. Okay, at 60 degrees. So you will have this shape, the blue color. The blue color is the output voltage. Okay, while the red color is the input voltage. Okay, so this is a positive cycle, and then this one is actually referring to the negative cycle. So you will have actually the full wave, okay, full wave rectifiers. Okay, so actually in these notes, we are always referring alpha in terms of degrees. Okay, okay, but alpha also can be given in terms of in unit time. Okay, so for example, if the voltage source here, the frequency is 50 hertz, the frequency supply is 50 hertz. So meaning that your period is 1 over your frequency source supply. Okay, so which is 1 over 50 hertz, which is given you 20 millisecond. Okay, so meaning that from here to here is actually 20 millisecond in time. Okay, and the degree is actually equals to 360 degrees. So full cycle 360 degrees, and the time period is depend on the frequency. So if the frequency is 50 hertz, then your period is 20 millisecond. Okay. So if the alpha is given, for example, in 30 degrees, what is the alpha in time? Okay. Then you need to use at 30 degrees. Okay. For one period, so 30 degrees of the full is 30. Okay. So you need to multiply with the full period, 20 milliseconds. So it will give you, okay, if you are using calculator, so 30 over 360 multiply with 20 millisecond, it will give you 1.667 millisecond. Okay. And if the alpha is 60 degrees, so what is the time alpha here? So 60 degrees over 360 multiply with the period 20 milliseconds. So it will give you, this one is berapa So 60 over 360 multiply with 20. So it will give you 3.3 millisecond. So meaning that for this is time. Sorry, this one is actually in degrees. So if this in time, so meaning that full cycle 360 degrees, the time is actually 20 millisecond. Okay, this one is 60 degrees, meaning that this time is actually 3.3 millisecond. Okay, so I hope you understand on how to do this conversion. Okay, so since the load is resistor, so meaning that the current shape will also following the shape of the voltage output. Okay, and then this is actually the equation of, for example, to calculate the average values. So right now, since this is a full wave rectifier, so your period is pi, okay? Because you can see every time, each pi, so it will actually repeat its waveform, okay? So your period is right now is pi. Okay, so and then you integrate from alpha to pi and then the function of the voltage. So you will have the equation is Vm over pi 1 plus cos alpha. So this is the average voltage. And this is the equations for the RMS voltage. So usually this equation do not memorize, okay? So usually the equation will be given. Okay, so do not memorize. And then for power absorbed by the load, you can use this formula. I think this one is should be V square. Okay, V square. Or you can also use this one, I out RMS multiply with resistor. But I think this one is much better. Okay, to be used instead of using this one. Okay. And the current. So this is the current through when you have a resistor load. So as you can see here, it's actually a linear. It's a linear relationship between V out and also I out. So just V out average that you have obtained, I need to divide by the resistor. Okay, resistor is actually a constant values, so you will have this average output current equation. And then this one is the RMS output current. Okay, so RMS. Okay. So meaning that if you want to obtain,
Doctor,
sorry, yeah.
the line is not clear.
Oh,
Voice kind of cut up.
itulah. That one is uncontrollable. I am very sorry because right now I don't know. So that is the problem that, that we need to face. I think for students and also lecturers. Sekarang ni okay tak? How about now? Putus-putus juga.
Right now it's okay. Last time.
Itulah. And I also heard that for those who have already inside UTM, the internet coverage, the stability of the internet in the college is also not very good. Itulah. Online. So I hope we can go for the face to face lah. Okay, face to face after Raya, and then so we can avoid this disturbance lah. Okay. Okay. I hope you can uh, memorize this formula, because this one will be used, okay, to calculate your power factors. Okay, we know that your power factor is P over S, right? Where P is actually you can get from I out RMS multiply R, and this one is V source RMS multiply with I source RMS, which is this one is actually multiply with I out RMS. Okay, this is very crucial because it will affect the calculation of your power factors. Okay. Okay, so we go for the example 4. I think this one is a very straightforward example. The control single phase bridge rectifier has a 20 ohm resistive load, and the voltage is 120 volts. So meaning that this one, if I draw 120 volt RMS, okay, full bridge. So usually put like this, okay, and then resistor is 20 ohm, and then the delay angle is actually 45 degrees. Okay, so this is symbol the SCR full bridge. The frequency, okay, the frequency is 60 hertz. Okay, determine the average load current. So this one you just use the previous formula, which is Vm over pi. Okay. Oh, I don't have with me my calculator. Tertinggal dekat rumah. So sorry, this one kan. This one 1 plus. I forgot to bring my calculator. So maybe one of you can calculate it for me. So Vm. So right now you need to convert your Vm is square root 2 multiply with 100 VRMS. So what is the Vm?
169.7.
Okay, 169.7. 1 plus cos 45 is 0.7, is it? Okay, let me see. 45.
1.707.
1.07.
1.707.
Cos 45 is 0.5253.
Okay. 0.525. Okay. Over pi multiply with resistance 20. So
The answer is 4.611.
4.611 amperes. Okay. And then the RMS load current. So this one. You need to use. Okay, sorry. VRMS. This one. Jangan Okay, please someone. Berapa tadi? 167. 169.7 over 20 ohm square root 1 over 2 minus 45. You need to convert, okay? To convert into a radian. 45 degrees. What is the radian? Because right now divided by 2 pi. So you need to convert pi this alpha into radian unit. 45 degrees is equals to
45 degrees is equal to
yeah.
wait ah, in radian.
Kali 2 kali
0.785.
0.7855, right?
54.
Okay. 0.785
854.
lah. Okay lah. 5 over 2 pi. Oh, aku tambah lagi ni. So kena panjang sikit ni. So 169.7 over 20 square root 1 over 2 minus 0.785 over 2 pi plus sine 2 pi. So sine 2 sine 2 alpha. So sine 90 degrees. So sine 90 degrees is 1 over 4 pi. Panjang.
The answer is 5.721.
5.721 amperes. Okay, sorry lah for the internet connection because that one is out of control. So you need to blame UTM lah for this. Okay, so I hope everybody get the same answer. Okay, so actually a very tedious work lah. So the answer is 5.71. Okay, so 5.721 amperes, and since we know that the RMS load current is same with the source current, so meaning that the RMS source current is also 5.721 amperes. And the power factors, as mentioned before, you can use P over S. Okay, so your P right now is I out square RMS multiplied with resistor over the VS RMS multiply with I source RMS. Okay, so this one is 5.721 square multiply with 20 ohm over the Vsauce RMS is 120 multiply with I source RMS, which is equals to the I load, which is 5.721. So you should get the answer.
Zero point 9535. 9535.
Okay, 95 okay lah. So quite high lah. Okay, you can see it's quite high. 0.95 is almost unity power factors. So it is lagging or leading. So right now you have the values 0.95, but whether it is lagging or leading, there is no information there. What is your decision, whether it is lagging or leading?
Lagging.
Okay lah, for this kind of power circuits, okay, usually rectifiers, usually the power factor is always lagging. Okay, even though there is no such information, because right now as you can, usually see that if the power factor is lagging, meaning that you have some inductor. Okay, but right now there is no inductor at all, but it is the power factor is lagging is due to the power the switches, okay, the SCR that injecting harmonics. Okay, I have already explained in the previous class about the harmonics. The harmonics will actually deteriorate the quality. So it will deteriorate the waveform, it will deteriorate the power factors and so on. Okay, so usually for this kind of circuits, so we always refer the power factor to be lagging power factors. Okay. Okay, so thank you very much on that. So right now we go for the RL load, which is much more complicated. Okay. So actually in the RL load, so we are using the same circuit. Okay. So right now this is control, which is using SCR, but right now the load is RL. Okay. So there are two type of condition that we will obtain when you are dealing with the RL load. First, we have the condition where the output is in continuous conduction mode, or CCM. We call it as a CCM. And the second one is the discontinuous conduction mode. Bukan continuous conduction. Continuous current mode. Okay, DCM. Okay, continuous current mode or discontinuous current mode. It depends on the alpha. Okay, both this condition, the output, okay, it depends on the alpha values and also your inductors values, or sometimes we also refer as a XL, which is you know XL is actually omega L. Okay, it depends on the values of the inductors. Okay, so we are still using the full bridge. Okay, and this is actually the waveform where this waveform is actually, as you can see, the current here, you have a positive current, and then this one is beta. After beta, you will see that 0 until the next alpha, and then the next alpha you will have a positive current. So as you can see, you have positive and then 0, and then positive again and 0. So this one what we call DCM, this continuous current mode, because the current is actually in this continuous condition. Okay, the current itself, the waveform is discontinuous. Okay, and this is actually the waveform of the voltage output. So you will have the extinction angle here. So you have here, and then until the next alpha, there is a 0 voltage here until you have a next firing angle, and then so on. Okay, so this continuous current mode is due to the small value of the inductor. Okay, small value of the inductor. And this one is a discontinuous current mode, and actually the analysis is similar to the half wave. Okay, but the alpha, the time you need to convert into, you need to change into the alpha. Okay, what is mean by this actually in terms of to obtain the V average, okay, V average, okay, VRMS, and so on. So actually, you use the same equation, but you need to change the period from 2 pi to pi values, okay? Because this one is the full wave rectifiers. Okay, why this happen? Why this happen? Why you have a DCM? And then you have extinction angle here and so on. Okay. So can we start our analysis at this cycle after this? Okay. So we start our analysis from this to this. Okay. So from here is 0. So meaning that because the firing angle is set here. So meaning that from here to here, there is no all this. Okay. All SCR are off. Okay. At this part. Meaning that between the input and the output, okay, all the SCR are off. Okay. All 4 are off. Okay. So meaning that there is no connection between the V out and Vx. So that's why we have 0 here. Okay. And then we consider this one is a positive cycle. Okay. So this one positive, and then this one is actually negative cycle. So positive cycle, for positive cycle, T1 and T2 on. Okay. T1 and T2 are turned on. Okay. Until pi. Okay. After pi, the cycle change to negative cycle. Okay. So at negative cycle, you should know that T3 and T4 should turn on. Okay. T3 and T4 should turn on. But both are not turned on because the alpha is still very far away from pi. Okay, because you give a delay angle, so you are not turning on the SCR T1, T3 and T4. But as you can see, the inductor here, it need to discharge the energy, right? You need to discharge the energy because at the positive cycle, it charging. Okay, until pi. So because the polarity is changed, so the inductor need to discharge the energy. Okay, but T3 and T4, it need to charge to 3T and T4, but T3 and T4 are not still not turned on because the delay angle is not given to them. So what this inductor do is actually it will discharge and force T1 and T2 to turn on, to remain on. Okay, so at this particular part here, okay, T1 and T2 are forced to remain on. Okay, at this part. T1 and T2 are forced to remain on. Okay, until the energy inside the inductor is finished. Okay, as you can see, until the energy inside the inductor is finished, which is the current is going to 0. So the meaning that the energy is finished, and then it will go back to 0 voltage. 0 voltage meaning that the circuit is not operating. Okay, so T1 and T2 is off. Together with T3 and T4 is still off. Okay, so meaning that the voltage output is disconnected from the input at this part. Okay, and then the cycle will actually repeat itself. Okay, so this is actually the part. Okay, so the crucial part from here, sorry for that, from here to here, all SCR off. Okay, so as you can see, From here to here, all SCR are off, and then this is a positive cycle. T1 and T2 are on. Okay, and then from pi to beta, okay, from pi to beta, T1 and T2 are forced to remain on because it need uh, to make sure that the energy from the inductor is fully discharged. Okay, until the energy discharged fully becomes zero, and then it turn off. Okay, T1 and T2 will turn off automatically because there is no force. Okay, so at this part, all the SCR will turn off. Okay, and then after alpha at negative cycle, so T3 and T4 are on. Okay, until here, and then till from 2 pi to here is actually T3 and T4 are forced to remain on. Okay, so because this one is actually positive cycle balik kan. Okay, so I hope you understand, and I hope during my explanation the internets are good. Sorry for that. Okay. Itulah UTM suruh student balik They are forcing the student to come in, but the facility is not good. So you need to blame UTM lah. Okay, so and then this is actually the equations that related to the DCM, okay? DCM, discontinuous current mode. And this is actually the condition. Okay, and then this is the formula of the current. So actually for the DCM, so as you can see, it's actually similar to the half wave. It's similar to the half wave RL. Okay, so the equation here from alpha to beta. So you can use this equation to calculate the current, and to determine whether your rectifiers are in DCM or CCM, you can use this condition. So this one is actually what you call condition 1, the first condition. Okay, you can use this formula, but usually since beta extinction angle is difficult to calculate. Okay, so usually this one is not very popular. Not very popular to be used to determine whether your rectifiers are in DCM or CCM. Okay. Okay, next is the condition of CCM. Okay, so this is the output current and output voltage when your rectifiers are in CCM condition, meaning that the current is in continuous mode. Okay, so as you can see, the current is always positive. There is no zero, so always continuous. So that's why the name CCM. Okay, continuous current mode. And the voltage also, as you can see, there is no zero voltage. There are either negative, okay, negative voltage or positive voltage. Okay, there is no zero voltage. As you can see here, we have zero voltage. You have negative, you have zero, and then you have positive. Okay, but for the CCM, as you can see, we have only zero negative voltage or positive voltage. Okay, so this one happen when your inductor is have a very large inductor. Okay. And since this is the condition, since this one, okay, continuous current mode, okay, so I think the analysis is very simple. Okay, so this equation is actually to determine the condition for continuous current mode. Okay, so I think you can ignore this one. So finally, what we'll actually conclude is actually to determine whether it is in CCM use this formula. So alpha must be lower or equals to the inverse tangent of omega L over R. Okay. So so this one is the condition 2. Okay. But this one is much more popular to be used. Okay. To determine whether your rectifiers in CCM or DCM. Okay, compared to the condition 1. So condition 1 is here, but since beta is very difficult to obtain, so this condition is much more popular to be used. Okay, so for CCM, use this formula, and to determine whether it is a DCM, so meaning that your alpha is larger than inverse tangent omega L over R. So as simple as that. So if your calculation, your alpha is larger than inverse tangent, so meaning that you know that your circuit will be in DCM. If your alpha is smaller than inverse tangent, so you know that your rectifier will be in CCM. So please use this condition, okay, to determine whether it is DCM or CCM. So to make sure that your rectifier in CCM, so make sure, okay, make sure your alpha is lower than inverse tangent omega L over R when you design a rectifier. Okay. And so this is actually the analysis to obtain the average voltage. Okay. So your V out should be like this. Okay. You need to familiarize your sketch, sketching on the output voltage, because your test one will be on sketch. So how you sketch the waveform and so on. So for CCM, your voltage output memang buruk lah. My drawing is not very good. Okay. So your equation for the output average is 2Vm over pi cos alpha. Okay. So if you want to calculate the V output average, use this formula. So this one is for CCM. Okay. CCM. Okay. And then so this is your V out. Okay. And then you know that actually your V out is contains the average values and some ripple, okay? Some ripple, which is the harmonics. So V out is, you can use this formula. Okay, and then to obtain the Vn, which is the V harmonics, you need to use this formula. Okay. You don't need to memorize, okay? All will be given if needed. Okay. So Vn is equals to A n square plus Bn square, which is what is An and what is Bn. So very complicated calculation here. Okay. And then the current. Okay, since we know that the current is this one is actually almost DC, meaning that you have I DC plus the summation of I harmonics. Okay. The harmonics is actually we refer as the ripple. Okay. So if this one is 0, meaning that your current is actually a pure DC current. Okay. But right now you have a ripple. So meaning that you are containing a DC current plus some harmonics, which is IN. Okay. So to obtain the IN, so this one, I think a very similar one. IN is Vn over Zn. Okay, so but what is Vn? Vn, as refer in the previous slide, is square root An square plus Bn square. Okay, and Zn is your impedance, depending on the numbers of the harmonics numbers. Okay, IO is your average, which is your VO is 2 VM over pi, I think cos alpha, right? For the half wave, for the full wave. Okay, 2 VM over pi cos alpha. So after you obtain the IO and IN, so you can get your IRMS. Okay, I output RMS. And for the full wave, okay, full wave rectifier, always the I output RMS is equals to I source RMS. Okay, so please be noted on that. I out RMS is always equals to I source RMS for the full wave. Okay, for the full wave rectifiers. Okay, so I think example 5. So I think we may take a break first, about maybe 5 minutes, okay, before we continue with example 5. And then after that, we continue with the 3-phase, okay. So can we have a break, 5 minutes, okay? So my time is 11:41. So we will meet again maybe 11:46, okay? 11:46. We start again, okay? So you can maybe disconnect first, and then at 11:46. Yeah, just enter the room again. Okay, guys. So I have shared with you example 5. Okay, I have shared with you example 5, so you can maybe download it first, and we can discuss. It's much easier through that, I think, rather than we uh, we do it online. So example 5. So I'm sharing the Microsoft Edge. So semua nampak Microsoft Edge ni. Okay. So the control single phase bridge sepatutnya this one tinggal ni. Forgot to put here. Full bridge rectifier has a parameter as follows. So supply voltage 169.7 sine 314 T volt, and the load is a is an inductive load where you have a 10 ohm, and then the inductor L is 20 millihenry. And the firing angle of the power device is 30 degrees. Okay. And you also have been given extinction angle, which is beta. Okay. So this one is your beta, and this one is your firing angle. Determine whether the load current is continuous or discontinuous. So we are using the second condition, because the second condition is okay. So we have two conditions, right? The first condition is actually what? What is the first condition? For this one, jap, saya tengok balik. What is the first condition? Okay, for DCM, your beta must less than alpha plus pi. For CCM, beta must less than alpha plus pi. That is the first condition. And then the second condition that we have already know is if we refer to the notes, okay, for DCM, alpha must larger than inverse tangent of omega L over R. And for CCM, alpha must be smaller or equals to the inverse tangent omega L over R. Okay. So I have mentioned earlier, condition 2 is much easier. okay, is more popular to be used. But since in these examples, we have been given the extension angle, so I think it's better to use the first condition. Okay, so check by using the first condition. The first question, determine whether the load is in CCM or DCM. So we are using the first condition. So alpha plus pi. So right now your alpha is 30 plus pi. So pi we know is actually 180 degrees, right? So this one will become 210 degrees. So your beta is 216. Okay. So meaning what? Your beta is 216 and your alpha plus pi is 210. Meaning that your, oh sorry. Yang ini, sorry for the first condition. Silap ni. 2 DCM. So for CCM, your alpha, your beta must be larger. Okay. Must be larger than alpha plus pi. So from here, from the first condition here, you see that your beta is larger than your alpha plus pi, meaning that your rectifiers are CCM. Okay. Okay. I hope you understand that. Okay, so your rectifiers are in CCM. So your analysis will be CCM analysis. Okay. So I have also used the second condition here. Okay, we can use the second condition. For example, in this solution, I use second condition. So alpha, which is 30 degrees, and I need to check with my inverse tangent omega L over R. So my inverse tangent omega over R is given me the answer 32.126, meaning that it is smaller than alpha. So that meaning that your rectifiers are in CCM condition. Okay. So for CCM condition, meaning that your output voltage should be like this lah. Okay. You have negative and positive only. There is no zero voltage here. Okay. And your current also will be in this shape. Okay. So that is your current. And this is your V out. Okay. So the second question is calculate the load voltage and the load current. So which is time consuming. So that's why I make it first. Okay. So for CCM, for this kind of voltage waveform, the equation is 2 Vm over pi cos alpha, right? So you can have these values, the 93.5 volts. Okay. So just substitute the alpha with 30 degrees and the VM is 169.7. Okay, you should get 93.5. Okay. And what else? Okay, so this is the load voltage. And this is actually the average load current. Okay. So V out over or V out average over R, so 93.5 over 10. Okay. Oh, I think we haven't finished this one. Determine, calculate the load voltage. I think if this one, I think this much easier if this one is actually average. Okay, average load voltage and average load current. Okay, so this one, 93.5. Okay, this one, 9.35. Okay, and then the last question is the power absorbed by the load. So power absorbed by the load, you need to use I square, okay, I out RMS square, which is, we know that your I out RMS square, okay, is equals to this one, this equation, okay, which is your I out average plus the summation of all your harmonics current, which is starting from n is equal to 2 and then 4, 6, all must be in even numbers. Okay, so next is to calculate all the uh, harmonics current. Okay, starting with I2 and then I4 and so on. So this one is this step shows you the use of the formula. I think this one okay. I think this one is not correct. Okay, Vn here. Okay, I think this one is not correct because Vn is, if not mistaken, is actually A square An plus Bn square. So where An is this one, right? If not mistaken, if can you refer to the notes, if not mistaken. So maybe I wrong. Yes, yes. So this is wrong. Okay, this is wrong. So I think I need to redo it again. So this one is actually for the half wave rectifier, if not mistaken. Okay. So if you refer to the notes, okay, I'm sharing with you right now. Share content. Okay. I'm showing right now the PowerPoint. Okay. Slide number 28, I think. So VN, okay, for the full wave rectifiers is this one. Okay, where it is AN and BN. So which is very time consuming there. So I think this one is wrong. Okay, so you need to use Vn this equation by using this equation. Okay, calculate all. Okay, the V2, V4, Z2, and Z4. Okay, so Z2 is actually, this one is actually referring to the N lah. So this one is also N. Okay, so N is equal to 4. So as you can see, every impedance for every harmonics is different. Okay, so this one Z2 is 16.05 and Z4 is 27. So the impedance is correct. The only that is not correct is actually the calculation of the voltage V2 and V4. Okay. So this one is correct. The step is correct, but the value is not correct lah. Okay. So from here you can compute your I out RMS. Then from here you can get directly the output power. Okay, but the value is not correct. So I will redo it again and maybe share with you after this. Okay, so actually the step is correct. The only that is not correct is the voltage. Sorry for that. Okay, as you can see. Oh, sorry, saya lupa pula nak share. Okay, betul eh. Okay. Oops. Okay. Okay, any question before we proceed with the three phase? And for three phase, just a brief, It's just a brief. Not very detailed lah for the three phase. Okay, so okay. So if there is no question, then we can go straight to the three phase. So I have already shared my three phase notes in the e-learning. Okay. So three phase rectifiers. So this is the circuit for the three phase rectifiers. So you should know, okay, the for the three phase connection, they have two connection, whether either delta or star. Okay, so it depends on the connection. So actually for this connection, as you can see for the supply, So we have an N here. So and then so this is actually a Y. Oops, sorry. So this one is actually a Y connection or star. Okay, sorry. Star connection, okay? Y or star connection. Okay? So meaning that your voltage V line is equals to or not equals to V phase for star connection. So for star connection, so your V line is square root 3 V phase, okay? And your I line is equal to I phase. Okay? And this one is actually AC to DC conversion, meaning that from AC to DC. So as you can see, we have a AC source, which is you have a three-phase voltage. The displacement between the phase is 120 degrees. Okay, every phase 120 degrees. Okay, and then it converts into a DC voltage. This one is a V out. Okay, as you can see, this one is your V out. The line, okay, is your V out. It looks like macam ada owning lah. Banyak. So phase and three-phase rectifiers, you will see that the three-phase rectifier has more DC waveform. Okay, not more DC waveform. Is more towards DC. Okay, more towards DC. Is compared to the single phase. So that's why actually in the rectification system, they always prefer to use a three phase for to rectify an AC. Okay, instead of using a single phase. Okay, but it depends on the applications lah. Okay, depends on the application. So if the application is single phase by hook or by crook, they need to convert by using a single phase rectifiers. So this one is your source. Okay, VAN, VBN, and VCN. Okay, and this one is your V output. So as you can see, for one cycle, okay, from here to here, one cycle, you will see that you have one, okay, starting from here, 1, 2, 3, 4, 5, and half here and plus half here. So you will have pulse, something called a 6-pulse rectifier. Okay, because in one cycle of a phase, you will have a 6 pulse. Okay, and from here, how to determine which diode will turn on? Okay, this is a diode. Okay, it's a control rectifier. So it depends on the circuit forward bias and reverse bias. So from here, how to determine which diode is turned on? For example, for the first pulse, this one for the first pulse. Okay, so how to determine that? So actually, okay, sorry. So since we have 6 pulse, and then we know that for one cycle phase is actually 360 degrees. So meaning that one pulse is equals to 60 degrees, okay? So as you can see here, one pulse is the period is 60 degrees. 2 pi over 3 minus pi over 3 should get the period is the angle is 60 degrees. Okay. So every pulse, the period is 60 degrees. Okay, so how to determine which diode is turned on? For example, we go for the first pulse here. Okay, so the numbers here 6, 1, 1, 2, 2, 3 is actually referring to the numbers of the diode. Okay, the diode number. Okay, so for the first positive pulse, a diode D6 and D1 will turn on. D1 and D6. So how to determine D1 and D6 is on? It's actually referring to the polarity of the sources. So as you can see, we have the upper group of the diode here, D1, D3, and D4. So all are numbered as a odd numbers. And we have another group, which is the lower group of the diode. We name it as in the even numbers. So right now at the first pulse, which diode is turned on? Okay, so you refer to this portion. Okay, this portion. So to determine the upper diode, which diode we turn on, we look at who
Doctor, we can't hear you right now. Your voice is like cut off. It's like totally cut off right now.
VCN. So this one is VC. And this
Oh,
waveform, yeah, is B. So this,
yeah, like your
yeah.
voice was the whole time.
I'm sorry for that because I don't have any control on that. The internet stability in UTM, I think, becoming very, very poor right now because I think most students are online in the campus. I'm sorry for that because I cannot. Maybe after this you can see my recorded video. Okay. Sorry for that. I know maybe there is a problem in the
Fine, it's fine.
internet stability, but I cannot help on that. Okay, which one has the positive values? Compare here. So right now, as you can see, A has the most positive values, right? Compared to phase B and phase C. And then you see that which diode is connected to phase A. So phase A here, so it's connected to D1. So that's why D1 is on. And to determine which diode is actually turned on at this lower part is by looking at which phase has the most negative values. So comparing A, C, and B, you will see that phase B has the most negative values. So we look at phase B and then the diode D6 is connected to it. So meaning that D6 will turn on. So that's why we have 6 and 1 is turned on. So that is actually how we determine which diode is turned on. Okay. And then this is actually the current. Okay. I can see that this one is, you can see as a I output lah. I out. Okay. So this one actually what I have already give to you. Okay. So right now your V out is like this. Okay. So the V out average, you can use this formula. VM line to line, okay? Line to line. So if you are being given V phase, you need to convert. Okay? So you need the V line to line is equals to square root 3 V phase. Okay? This formula also you need to know. Okay? And then the V harmonics, which is the ripple here. Okay? So you can compute by using this formula. And the number of harmonic is starting from 6, 12, 18. So it jump 6. Okay? 6. So every 6 harmonics, so you will have appear another harmonics. So and then this one is your average current. Okay, current to the load, which is you can use this formula. Same, okay. So this is harmonics term, and then this is your DC term. Okay, and then this is actually how we calculate the I average, okay. I average. This is the diode average. This is the diode RMS, and this is the I source RMS. So the relationship between I source and I output is actually by using this equation. So this is a waveform, two waveform that shows that this is the current for a resistive load. So as you can see, this one is your I output. You have a ripple. But when your load is actually highly active load, okay, meaning that your omega is larger than your resistor, so you will have a pure DC current, meaning that your IN is 0, okay? All your harmonics current is 0. This one you have I out plus summation of IN. But for when you have omega L is much larger than resistor, your harmonics is 0. Okay? And I think this one we can skip. Itulah susah. It's very difficult for online ni if the lecturer stability internet is not okay. It's quite challenging lah. Okay. I don't know whether you can hear me or not. You can hear me or not. So I hope some of you can still hear me and still with me. I know because when the internet stability is very poor, so your interest in hearing the lecture is become very low lah. It's such a logic kan. Memang kita tahu gitu. We understand. So itulah UTM need to do something lah. Okay, so this is saya pun sebenarnya macam dah malas nak mengajar dah ni. because when I heard that you have problem hearing my voice, so it's quite difficult to motivate me to lecture. Okay, so okay, never mind. So we need to continue this. Okay, so this is so we have already finished with the diode rectifiers 3-phase. So this one is SCR, okay, control rectifiers. So actually the control rectifiers, you can see how we determine the angle, which is your alpha here. So this is the variation alpha. So it's from here, okay, from here. So starting from here, so this is what we call your angle, 30. So if there is 60 degrees, so meaning that you full cycle, okay, full cycle. So because we know that one pulse is 60 degrees. So if you are delaying 60 degrees, so you miss this one. So So actually, if the 30 degrees, so meaning that your voltage waveform is this one. Okay. But if you are delaying to 60 degrees, you will see that your voltage is like a shark fin. And if you further delay, okay, your alpha, which is this one, 60 plus 30. Okay, this one 60 plus 30. So you will see that you have some negative part here and then another positive part. So that is actually the variation of when you delaying your alpha values. Okay, and this is actually a waveform that shows when alpha is 45 degrees. Okay, so from here to here, meaning that from starting from here to here is 45 degrees. Okay, so this is when your load is R load. Okay, so this one is R load. So same, the output voltage is actually the equation for the output voltage is like this. You have DC terms and also the harmonics term, which is AC. So same, the harmonic is actually starting from 6, 12, and 18, and so on. You just just add six numbers there. Okay, and then the equation for the output voltage is this one. You add up with a cos alpha here. And the current also same. So you have IO plus the summation of IN. Okay. Which is the same. I think no problem on this. Okay. And I think example 2 is this one. I think this is the solution. You have already the solution here. You can refer to. And I hope so. So for your homework, okay. So please do this example 2, and then there is a solution here, so you can refer to the solution. Okay, rather than we discuss in the class. So I think since the internet stability also not very good, so I think I give this example 2 for you to do the homework. Okay, and compare your answer with the solution. Okay, so I think we finish on the 3-phase rectifiers. So in our next class on Thursday, we will go for the DC motor drive using rectifiers. But before that, please, before we start our class on Thursday, so please watch the videos about the principle of the DC motor. Okay, so I have post a video, a 3D video from YouTube. So that explain about structures, the basic principle of the DC motor, so that you can understand, okay, about the how the DC motor drive using rectifiers control the speed and the torque. Okay, so I don't want to explain back about the structures, the basic operation of the DC motor. So on our class on Thursday, so we just move on, okay, continue with the introduction of how we use rectifiers to control the motor. So it's very crucial, it's very important you watch the video first. Okay? So I think that's all from me. So please do this homework, but do not submit. Okay, please do not submit. Just do this homework, your own homework. Okay? So I think that's all from me. Any question? Okay, sorry lah for the internet stability. That one is out of my control. So maybe you can watch again in the YouTube lah. I will upload this video in the YouTube. Okay. So for that, thank you very much for your understanding and attention throughout these 2 hours class. Not 2 hours, 1 hour and plus, right? So we meet again on Thursday, insyaAllah. Okay, so Assalamualaikum and have a very good day.
Thank you, Doctor.
Okay.
there.